let me get rolling on that.
He said he can't hear
And
you.
how can I full screen that?
Mr.
So
Norris?
without image made, I can do this for sure. I'll do that. I think that's the best I'm going to be able to do. Okay, so section 1.6 has a pretty ominous title. It's called Other Types of Equations. That's pretty daunting because, you know, we've only looked at like two types of equations, one variable linear equation, one variable linear equations and one variable quadratic equations. There are literally millions and millions of other types of equations. It should say a few other types of equations. There's really three other types of equations we need to look at from this section. Now, this first problem I'm going to do is not exactly like one of those three types, but it is very similar to a homework problem. I know this because our Monday night class, some of them were working on homework and a couple had looked ahead and had seen a problem like this. So you're going to see one similar to this in homework. So we're going to work it. There's not one like this on the test, but just for homework purposes. By the way, I have changed the due date on the homework to October 16th, which is the day we take our test. So the thing you'll notice about this equation right away, it doesn't just have x to the first power, and it doesn't just have x to the second power. It's got an x to the fourth power term, right? Which means this is not a quadratic equation. Technically, fourth degree equations are called quartic equations, which should make sense because, you know, 4 quarts in a gallon, 4 quarters in a dollar. It turns out that what we can do with this problem is think about what we did with the quadratic equations. I am first going to set this equal to 0. So I'm going to subtract 32x squared on each side. Everybody with me there? And so when I do that, on this right-hand side, you know, it all cancels and I just have 0. And that's what I want on one side. Notice these are not like terms, so I can't actually combine them, right? So I've just literally got 2x to the fourth minus 32x squared. To solve this problem, we're going to have to kind of think a little bit beyond just, okay, I memorized how to do this step and this step and this step. We got to think about what's going on here. And one thing I see is, and hopefully y'all do too, do y'all see that each of these two terms has 2 as a common factor? And we certainly got 2 here, and 32 is 2 times 16. And also, do you see that each of these two terms has x squared as a common factor? Because x to the fourth is x squared times x squared, right? So 2x squared then, 2x squared is the greatest common factor for that polynomial, for that expression. And I can factor that out. This is actually the easiest kind of factoring, just factoring out a greatest common factor, because all you're doing literally is distributing backwards. If I factor out 2x squared, which is the greatest common factor, then all I have to do is figure out, okay, what would I have to distribute 2x squared to get 2x to the fourth minus 32x squared back. And it should be pretty easy to see that I would need to multiply 2x squared times x squared to get 2x to the fourth, right? And then I would need to multiply 2x squared times what to get negative 32x squared? Not quite 16, but close. I don't want to get plus 16x squared. I want to get plus 32x squared. I want to get minus 32x squared. So it'd be negative 16. Do y'all agree? Everybody with me there? So do y'all see that if I were to distribute this 2x squared, I would get back where I started from? So this is factored correctly. Now what we can do is remember what we learned in section 1.5, which is when you've got an equation set equal to 0 and you factor that equation, then anything that makes any of these factors 0 will also make the entire thing equal to 0 and therefore solve the equation. So if you look at it, we've got this factor, 2x squared. What would I replace x with so that 2 times that number squared is equal to 0? 0, right? That one's so easy, it's almost hard, right? If I plug 0 in for x, 0 squared is 0, 2 times 0 is 0. So 0 is what makes this factor equal to 0. That tells me that 0 is a solution to that original equation. Now this second factor, x squared minus 16, we need to figure out what makes that equal to 0 too. And there's more than one way to do that, but the easiest way to do it, probably based on what we did in section 1.5, is to say, look, I need to figure out what value or values of x makes x squared minus 16 equal to 0. I actually could factor this. It's a difference of squares. I could factor it as x plus 4 times x minus 4. And if you're comfortable doing that, that's a quick and easy way to do it. What we did with problems like this in section 1.5 is we used that square root property where we just get x squared by itself on one side and then take the square roots of both sides, right? So I could just add 16 on the left side, add 16 on the right side. That gives me x squared by itself equals 0 plus 16 is just 16. And remember, if I take the square root of x squared, that's just going to give me x, which is what I'm trying to find. But remember, that means I also have to take the square root of the other side. And this is important because you won't find all the solutions if you don't remember this. Remember, 16 has both a positive and a negative square root, right? So the square root of 16 is 4. But negative 4 is also a square root of 16. Do y'all see? So those are also solutions to the original equation. So our solutions are 0, negative 4, and positive 4. Now, one thing that we'll have to learn, particularly when we get to chapter 3, this is important, so I'm going to go ahead and mention it briefly now. Remember, we've said a few times that when you have like for instance, this is a 4th degree equation, we would expect there to be exactly 4 solutions, right? The degree of the equation tells you how many solutions it has. But what that fundamental theorem of algebra says is that it has 4 solutions, but they're not necessarily all distinct. So I want to make sure y'all see what happened here. If I factored this 2x squared times x squared minus 16, as far as I possibly could, I would have 2 times x, because that's x squared, right? Times x plus 4 times x minus 4. So notice, if you look at what this thing would look like if you literally just broke it all the way down as far as you could, here's a factor that I can make 0 by replacing x with 0. And here's another factor that I can make 0 by replacing x with 0. And here's a factor that I can make 0 by replacing x with negative 4. And here's a factor I can make 0 by replacing x with positive 4. And of course, like I say, we could have factored this thing like I did here to find those 2 numbers. We just did it a different way, y'all see? But we still found them. But the thing to see is there kind of are 4 solutions, right? It's just that 0 sort of counts as a solution 2 times because really the factor that causes x to be a 0 kind of happens 2 times. Y'all see that? So really what the fundamental theorem of algebra says is if you count every solution each time its factor appears in the problem, then the number of solutions will always add up the degree of the equation. Everybody see that? Okay, with all that said, there is not one like that on the test, but there is one like that in the homework. There is one like this on the test, and we're going to do a couple of these. So I just call these square root equations. It's an equation that involves an expression under a square root symbol. So let me remind you, in fact, we just did something like that. When we had that thing a minute ago where we had x squared equals 16, remember what we did is we took the square roots of both sides, right? And the reason we did that is because we know that the square root of x squared is just x, and that's what we're trying to find. It's kind of like a square and a square root sort of cancel each other out, right? And of course, you know, whatever you do to one side, you have to do to the other. Well, here, kind of the opposite thing is happening. So we know that we can take the square root of both sides of an equation. We also could square both sides of an equation. And so here's why I might want to do that. Because if you look at this before I drew the parentheses and squared those sides, the problem in solving this equation is going to be that I've got this x trapped under this square root, right? Like if I'm going to find x, I'm going to somehow have to get rid of that square root, because otherwise I can't talk about x. I can talk about the square root of x. But if I square this, just like here, when we took the square root of a square, the square and the square root just kind of canceled out and gave us x. The same thing happens here. If I square a square root, the square and the square root just kind of cancel out. It just gives me x plus 3 without the radical. Y'all see that? But if I square one side, I have to square the other side as well, which should make sense at this point. We figured out, you know, you got to do that thing where you keep the equation balanced. Whatever you do to one side, you do to the other. But here's where most students miss this problem. This is not a hard problem at all. If you can FOIL, and if you can do the problems in section 1.5, this is an easy problem, but almost everybody misses this because they say that this x minus 3 in parentheses squared is x squared minus 9, or maybe x squared plus 9. It's actually neither of those things. And so here's what you've got to remember to get this problem right. X minus 3 in parentheses squared doesn't just mean x squared minus 3 squared. It means x minus 3 all squared. X minus 3 multiplied times itself. In other words, FOILed with itself. Everybody see that? And when we do that, notice we're going to get x squared. We're going to get outside part. That's going to be minus 3x, right? The inside part, negative 3 times x, that's another minus 3x. And then we're going to do last times last, negative 3 times negative 3 is positive 9. And what you got to watch out for is, because intuitively we want to just say it's x squared minus 3 squared and maybe get this, because that's intuitively what we want to do. If we're not careful when we FOIL it, we'll think these cancel, but do y'all see that they don't cancel each other?
Why not negative 3 minus?
They would cancel each other if one was minus 3x and one was plus 3x, right? Y'all agree? Everybody with me? But they're not. They're minus 3x and minus 3x. And negative 3 minus 3 is negative 6, not 0. Y'all see that? So what I'm going to get is x squared minus 6x plus 9. So again, that's the danger point in doing this problem. It should be easy to see that we're going to need to square each side. And this left side was easy to square because the square and the square root just cancel each other. You just get what was under the radical. But on this right side, if there's two terms like this, you got to multiply it times itself to square it. You just want to FOIL and make sure you combine the like terms carefully, right? Once you do though, this is a second degree quadratic equation. And we know that when we have a quadratic equation like this, we want to set it equal to 0 and then solve it. And so what I'm going to do is move all the terms to whatever side the x squared term is on. So I'm going to subtract x on each side. By the way, I'm also going to move this 3 to the other side, right? So I might as well just go ahead and subtract 3 while I'm at it. Everybody see that? And so you can see what's going to happen on this x squared side. I'm going to have x squared, negative 6x minus 1x is negative 7x. So x squared minus 7x, 9 minus 3 is positive 6. So I get x squared minus 7x plus 6 equals, and of course on the other side, everything cancels, we get 0. That was our plan. So now, when you have a problem like this, if you couldn't figure out how to factor this, you could always use the quadratic formula, but this thing is really easy to factor, so I would factor it way faster. And if you just take the time to practice this kind of factoring, you're way less prone to mistakes if you think about what you're doing. So we know we got to start with x and x. Now, y'all got to always, you have to think about this every single time you factor one of these. These last two numbers multiply to be positive 6. Right away, I know they have the same sign because they can multiply to be positive 6 if they have opposite signs. They may be both positive, but you can't guarantee that. They could be both negative. The way we decide is we look at the middle number, it's negative 7. Remember, those same numbers that multiply to be positive 6 have to add to be negative 7. So it should be easy to see that the numbers have to be minus 1 and minus 6, right? Because negative 1 times negative 6 is positive 6, which is what it's supposed to be, and negative 1 plus negative 6 is negative 7. The middle number, which it's supposed to be. Everybody with me? And so we have two solutions to this equation. What are they?
1 and 6.
1 and 6, I agree. Positive 1 because 1 minus 1 is 0. And positive 6 because 6 minus 6 is 0. Now, here's the other place students miss this problem, and it's a shame if you get here and still miss the problem, because it is still possible to miss the problem. So here's the original equation. The square root of x plus 3 equals x minus 3. So we got these two solutions, 1 and 6. Let's check our work and see if, make sure we haven't done anything wrong. If I plug 1 in here in place of x, so I'm going to plug it in here and here, y'all see? When I plug 1 in here, 1 plus 3 is 4, and the square root of 4. So I'm going to check x equal 1. So when I plug that in, 1 plus 3 is 4, so I have the square root of 4 equals, if I also plug 1 in here, 1 minus 3 is negative 2. Is that statement true? Isn't the square root of 4 equal to 2? Notice I don't have the minus in front of the square root. They didn't have the minus in front of the square root in the problem. So this is just going to be the square root of 4, which is positive 2. But on the other side, I got negative 2. Do y'all see that? Then 1 is not a solution to the original equation. And that's the equation we're trying to solve. Do y'all see that? We'll talk about what went wrong there in a minute, but let's go ahead and check 6 right quick and see if it works. So let's check 6. So if I plug 6 in here in place of x, 6 plus 3 is 9, so I'll have the square root of 9, and of course we know that's 3. On the other side, when I plug 6 in, I'll have 6 minus 3, which is 3. 3 is equal to 3, right? So 6 does make the equation true. And that turns out to be the only solution. Do y'all see that? Okay, let's talk about what went wrong with 1 here. Because if you look at it, you might go, well, what did I do wrong? Because it said 1 was a solution. You didn't do anything. The problem is The method that we have to use to solve this type of equation sometimes introduces what's called an extraneous solution, which means something that looks like a solution but really isn't. And so here's how you've got to think about problems like these square root problems. When you get here and you get these numbers 1 and 6, what you have to say to yourself is, okay, what I have learned so far is if this original equation has any solutions, 1 and 6 are the only candidates. 1 and 6 are the only numbers that might be solutions of the original equation, but you still have to check them to see if they are. I'll tell you what went wrong with this problem. So remember, at the very beginning, we squared both sides, right? Okay, y'all take a look here. When I plugged 1 in and I got this statement 2 equals -2, which is false. Remember what the first thing I did was, everybody look up if you're looking down at your notes. The first thing I did was squared both sides of the equation. Now, 2 equals -2 is just a false statement. Do y'all agree? But if I square both sides of that false statement, 2 squared is 4, that's equal to -2 squared, which is also 4. So the original statement was false. But if I square both sides, it turns my false statement into a true statement. Do y'all see that? But that doesn't change the fact that the original statement was false. So in other words, when we find these numbers 1 and 6, we have correctly solved this quadratic equation. But you have to remember, this is just, in this problem, this is just a tool we're using to help us solve this equation. And so only solutions of this equation that also make this one true are really solutions, right? So y'all always got to watch for that. I've got another one that's very similar to that for us to do, just so we can see that happening, where we can see that that happens pretty regularly. So here's another problem. Doesn't look exactly like that last one. Oh, Sulphur Springs. What's going on with Sulphur Springs? It says they have a hand raised. Oh, hang on, let me go back.
That has a hand raised.
Yeah, let me see if I can go back and find out what's going on. Glasses, chat. Are you kidding me? Okay. Paris, Christopher, I'm looking at Christopher. Wave at me if you can hear me. Okay, y'all sent me a little text message over this that says the audio is not working. Is it working or not? Oh, I can't hear you.
He can hear you.
But I can't hear you. I'm not hearing you. Let me try turning the volume up a little bit and see if I can hear you. I think turning that volume up is what's making me echo. But I think turning it down is what's making me not hear them. Let me turn my volume up a little bit.
Can you hear us?
Okay, so Springs, talk to me. I mean, Paris, sorry. Paris, talk to me and see if I can hear you.
Can you hear me now?
Yeah,
Hello?
can y'all hear him enough to make out what he's saying?
Yeah.
Okay, I can. You're going to have to speak up because I'm trying not to turn the volume up as loud as I had it, because I think that's what was making me echo back. I think what's happening is my sound is coming through y'all's speaker and running back through y'all's microphone or something. You know what I'm saying? Okay, so you were on that last problem that you wanted me to talk about, the 9 and the, I'll come back to that in a minute, okay? So where y'all had that question, let me see if I can find that.
What?
Why would you go on?
I may have to get them to help me figure out where we're at. So y'all, let me see what that question was. Where you're getting the square root of 9 and the square root of 4. Ooh, I see where I got the square root of. No, I don't. Y'all tell me where I had the square root of 9 and square root of 4. Can somebody tell me that?
It's at the last problem we did, when we did the solutions.
That one?
Yes.
Oh, okay. Okay. I got you now. Here's where I got these from. Y'all look. You get a clean piece of paper. So on this last problem we did, oh, I messed that up. So yeah, before we move to this next problem.
We now cannot see the problem.
Hmm?
We now cannot see the problem.
Oh, let me turn it back. Yeah, but they can, and they had the question. I'm just kidding. Oddly enough, they can see the document camera when we're seeing them, but we only see the document camera if we're not seeing them. It's weird. Okay, y'all. So this was our original equation, right? And when we solved it, when we went through this process and solved it, we found we learned possible solutions, 1 and 6. And so what I was saying is, when you solve one of these and you get these solutions, you have to test them and see if they work in the original equation. So what I did, where I got that square root of 4 and square root of 9, is what I did is I checked my work. So the first thing I did is plugged 1 in here in place of x. And so what I actually had was the square root of 1 plus 3 equals, well, I also plugged 1 in here, 1 minus 3. And so when I did, that gave me the square root of 4 equals, well, 1 minus 3 is negative 2, right? But the square root of 4 is 2. And 2 is equal to negative 2 is a false statement. So that means that 1 does not solve this original equation, because when you plug it into the original equation, it leads to a false statement. So that one's out. And then I did the same thing with 6. I plugged it in place of x on the left side. So that would give me the square root of x, which is 6 plus 3 equals, and then over here, I plugged 6 in, which gave me equals 6 minus 3. But when I did that, that's the square root of 9. Square root of 6 plus 3 is square root of 9. And of course, 6 minus 3 is 3. And the square root of 9 is equal to 3, right? 3 is equal to 3. So that's how I knew then that 6 was the correct solution. Does that make sense? So that's all I was doing
Yes.
where that square root of 4 and square root of 9 came up. I was just checking these two numbers that we found to see if they actually worked. Okay.
So when you factor it, are you just saying to basically check the work every single time so we know if one of those
Okay.
are not the answer?
That's a good question, and we're about to look at another example, so we might see if that same situation happens again. I think what she's asking is, am I saying that every time we do one of these, we're going to get 2 answers and only one of them is going to work? I'm going to say that that might not happen every single time, because it's always dangerous to say always or never in math unless you can prove it's always or never. And I can certainly find an example where sometimes you only get one solution, you don't even get 2 solutions. I don't know if there's a time where you get 2 different solutions and both of them work. But I will say this, it should make sense that if you get 2 solutions, one of them probably won't work, because you can see what's causing our problem here. It's because we're squaring both sides of this equation, and when you square, you lose a piece of information. See, you can always, no matter what 2 numbers you pick your favorite number. 7 is equal to 7, but 7 is not equal to negative 7, right? And so what's happening is we're finding 2 different solutions, but one of those solutions, if you plug it into the original equation, is going to lead to something like this. When you square it, it's true. Well, we squared it, so it made us think that was going to be a solution. So the upshot of that is, I think you can always expect, for the problems we're going to see, that if you get 2 solutions to one of these square root problems, you better check them, because one of them is probably not going to work. This one, by the way, looks a little bit different than the other. The last one we did. What looks different is the fact that we've got this square root expression, but we've got something that's not under the square root over there with it. Do y'all see that? We never want to, so you know what we're going to ultimately do is square both sides of this equation. We do not want to square this until that square root expression is by itself. So does everybody see that the first thing I've got to do is add 7 to each side? Everybody with me?
Is this a new problem?
It is a new problem.
Okay.
The last one was the square root of x plus 3 equals x minus 3. So this problem, what's a little bit different than the last one is, before I square both sides, I've got to make sure that I add 7 to each side of this equation, because that's going to give me this square root expression, the square root of 2x plus 13, by itself, isolated on one side of the equation. And of course, on the other side of the equation, I'm just going to have x plus 7. Now that I've got that square root expression by itself, I'm going to square both sides. And again, the left-hand side's easy. The square and the square root just cancel, and I just literally get 2x plus 13, the expression that was under that radical. On the other side, I've also got to square that. Now, remember what that is. That's x plus 7 times x plus 7, and you have to FOIL that with itself. And y'all ought to be able to FOIL it at this point. When you do, you should get x squared plus 14x plus 49. And if you're squaring it and you don't get that, wave a hand and we'll see if we can figure out what went wrong. But y'all should get that if you FOIL it and combine the like terms. So now this kind of looks like the last problem. Once we squared both sides, we've got to get all the terms on the side that's got x squared on it. So we'll subtract 2x on each side. We're also going to go ahead and subtract 13 on each side, right? So when we do that, on the side that's got x squared, we're going to have x squared. 14x minus 2x is what? Positive 12x. So x squared plus 12x plus 36, right? 49 minus 13 is 36. And of course, on the other side, everything cancels, and we get 0. Oh, this is going to be kind of an interesting one. When we factor this, everybody see if you agree with this. Well, somebody just tell me, when I factor this, what am I going to get? How does it factor? X plus 6 and? That's correct. X plus 6 times x plus 6. Do y'all see that? Notice that 6 times 6 is positive 36. 6 plus 6 is positive 12. So that's factored correctly. Do y'all see that this one is only going to have one possible solution? It shows up 2 different times, right? There are 2 factors here, but each factor leads us to x equals negative 6 as the solution. So this time we didn't get 2 possible solutions. That's just coincidental because we happened to get something that when it factored as some factor times itself, right? We still should check it. I'm going to predict that it works because, again, Olivia was asking, is this kind of thing always going to happen? Well, I should have had the minus 7 on the other side, but we'll just check it here. Because Olivia was asking, is that thing always going to happen? I think for all the problems you see, if you get 2 different solutions like this last one we did, it's pretty much always going to be true that one of them works and one of them doesn't. I also think it's true that when you do this and you get this situation where you only have one possible solution, I think we're going to see that it always works. But I've not mathematically proven that it always works. So I don't want to say that. I'm just going to say that every problem I've ever done like this, and I've done a lot of them, it always works. But you don't have to take that on faith. Just plug it in and check it, right? If I plug -6 in here in place of x, 2 times -6 is -12. -12 plus 13 is 1. So I get the square root of 1. And on the other side, when I plug -6 in, I get -6 plus 7. Do y'all see that is a true statement? Because -6 plus 7 is 1, and the square root of 1 is 1. So -6 makes the original equation true, so that's our solution. Do y'all see that?
Have the 7 on the other side of the x.
No,
When the problem-
okay, so Paris, what she's asking is, do you have to have this 7 over on this side with the x? I'll say 2 quick things about that. First of all, remember, this was the original equation. To solve this equation, you're going to have to move that -7 to the other side.
I did it with the 7 in it, and I still got.
Well, if you did, I'd love to see your work, because let me show you what you would really have to do if you did that. So Paris, I know y'all can't hear both sides of the conversation here, but I think what she's saying is she did it without moving that -7 to the other side, and she got the right answer. If you do it,
So I didn't do the square root part.
yeah, this is what I want to figure out is how did you get -6 if you didn't
I
do
the
it?
equation, I didn't do the square root part, but I did get -6.
But how did you do it?
I did 2 times -6 plus 13 minus 7.
2 times 8 is 6.
No, 2 times negative.
So what you're saying is you just guessed numbers till you figured out what probably went in there.
Well, don't you have to plug in the -6 to the x?
Yes, you do, but how did you know to plug -6 in? I'm saying, you're saying that when you solved this equation, you didn't move this -7 to the other side.
No, because I just assumed we keep it with the regular equation.
Okay, so I guess here's what I'm trying to get at. I guess all I'm asking is, you somehow figured out that you should replace this x and this x with -6. And then when you did, you saw that made the equation true. I'm just trying to figure out how you knew that -6 was what you needed to replace it with.
I thought whenever we find out the solution for that equation, we plug them into the x.
Okay, timeout. I think we're saying 2 different things.
Why don't you just let her show you her
Here's
work?
what I'm asking. How did you solve it in the first place? How did you find the -6 number? Because the way I found it is I added 7 to both sides and then squared both sides of that equation.
Yeah, I'm talking about the solution at the bottom for
Are you
that.
saying? we should run this
You're just talking about checking your
Yeah,
solution.
checking it.
Okay. There, the thing I would say is I really should have used this to check it.
Yeah.
Because that is the original equation, right?
Yeah.
And what if I made an arithmetic mistake when I added that 7 to both sides? For instance, I know someone in this room who has done this a time or two, and I'm not going to call names, but you'll probably know who you are. I know somebody in this room who has a time or two been solving an equation, and like they would, not thinking, they would subtract 7 on both sides and go, okay, that cancels over there, but you have to add it, right? And so it is possible, I'm just saying, and by the way, that person knew what they were doing, they just weren't thinking. And that happens. That's why we check our work, one of the main reasons. So you could have made a mistake when you went from here, to here. So actually you should check it here. I just had already written it down before I thought about that. And because I know that I'm a math whiz and I knew I had not made a mistake when I went from the original to this, I just said, I think I said at the time, I really should write it the way it originally was, but I've already written it and I just did it. But if you do,
Do you mind-
and you plug in,
do you
this
mind
is what
just-
you really should check it in. And when you do, you're going to get -12 plus 13 is 1. The square root of 1 is 1. So you got 1 minus 7. And you plug -6 in over here and it still works, right? So -6 is the solution. Yeah, you really should check it in the original version. I'm sorry, I didn't get what you were asking me. Like at first I thought that might be what you were asking, but then you said that you solved it without moving that over.
Yeah,
That's
so
what I
I'm trying
couldn't
to figure out
understand.
I thought you were solving it right there with the x plus 7 on the other side. What were you doing there?
That's where we were getting it ready to solve. Here,
Yeah, there.
I've already solved it. I just want to check that answer and make sure it works. And you're right. I should have plugged -6 into the original version of the problem. The only
Mr.
reason to
Norris, I
do
have a
that is
question.
because what if I made a mistake when I went from here to here? You see what I'm saying? So do as I say,
I have-
not as I do. Yes,
Paris has a question.
I hear them. I just can't hear what they're saying. What's the question?
Okay, whenever you have the square root of 1, is that because the original is -1 and the square root of -1 is 1?
The square root of -1 is I, first of all.
Well, that's what I was
And
confused
second
on.
of all, remember what I'm doing. I am plugging, remember our solution here was -6. Once I get here, all I'm doing here is checking my work.
Yes, if you go to the other paper that you had with the original equation that you just last
Yeah.
did, you just put 1 minus 7, so you didn't really explain kind
Well,
of
but
how
I
you
just,
got the
because
1.
I assume that everybody in their heads can say that 2 times -6 is -12 and -12 plus 13 is 1. And we all know that the square root of 1 is 1. Because
Okay, I was really
if I
confused
write
on the
out
very
every
first
single
one we did,
step,
so.
if I write out every single step all semester, we're only going to get about halfway through chapter 2 in this class. But that's what I
I didn't
did.
need you to write it out. I just needed you to explain verbally how you got the 1, because there's all of these check works and like the square roots, and
Yeah,
so I just
just
wanted
know
you
that
to
we're
explain how
plugging,
you got
okay.
that.
Okay, just know that we're plugging our solution into the original equation in place of x, just to check and see if we get a true statement, right? Everybody good? Okay. All right, so these problems are not that hard, really. You just got to know that, you've got to have that square root expression by itself on one side first. You got to square both sides, and you got to remember that when you square both sides, that means whatever's over here, you have to FOIL it with itself, right? You solve that quadratic equation, every solution you find, like in this first problem, we found 2 solutions. We have to plug both of them into the original equation to check them, because there is a very good chance one of them will work and one of them won't. Even when you just get one solution. Now, again, in my experience, every time I've ever solved one of these where you get one solution, kind of that repeated solution, it's always worked. But I've never proven that to be true, and I've never read anywhere that it will always be true. So my advice would be, anytime you solve a square root equation, plug every proposed solution into the original and make sure it works. Everybody good there? Okay, and we're going to see another one of those, of course, when we go through our practice test after a while. Okay, this equation, now that first one, very first problem we looked at where there was a 4th degree and a 2nd degree x term, and I said there's not one like that on the test. There is one like this on the test. So we want to make darn sure we know how to do these. I'm going to show you all that there's more than one method for solving these. And if you know another method, feel free to use it. I'm going to show you the method that, to me, sort of simplifies the process the most. And we're going to look at a couple of these problems. So first of all, before we even start working on this problem, does everybody agree that x to the 4th power is the same thing as x to the 2nd power raised to the 2nd power? Do y'all agree that that statement's true? Because x to the 2nd power squared means x squared times x squared, and that certainly is x to the 4th. Do y'all agree? There's a reason that I want to think that way, because if I say that x to the 4th is the same as x to the 2nd squared, then this equation looks like this. I just put the x squared in parentheses here for emphasis, because what I want us to see is when I turn that x to the fourth, when I write it as x to the second squared, what I've got is some parentheses raised to the second power minus 13 times those same parentheses. And do y'all see that there's a goofy way to say it, but it's true. This is the same as x squared to the first power, right? Plus 36 equals 0. So this is not quadratic. Again, it's quartic. But there is a way to kind of look at it where it's like, well, I do have something squared minus 13 times that same thing plus a constant equals 0. Here's why I want to do that. I am going to do what we would call I'm going to make a substitution. If I can spell substitution at least. I am going to let u equal x squared. So let me tell you all what I'm doing and why I'm doing it. And by the way, you don't have to use the letter U. It's just that U is a letter that's commonly used. U and V are commonly used as letters that we use for variables when we make, quote, substitutions. What I'm going to do is I'm going to look at this equation, which is just this equation, but I've written it so I see all these x squareds in here. Everywhere I see an x squared, I'm going to replace that x squared with u. So I've got x squared to the second power, but I'm going to replace x squared with u, so that will give me u to the second power. Everybody see that? All I'm doing is replacing this x squared with u. I know that seems weird. It may not seem like there's a good reason to do it, but trust me for now and just say, I want to see everybody see that's what I did. That if I do replace this x squared with u, that's going to say u squared, right? Minus 13 times, here's an x squared, but I'm going to replace that x squared with u. So that's going to become minus 13u plus 36 equals 0. Now I'm aware that this isn't the original equation. I mean, I'm not even using the same variable for the letter. And I don't have the same powers on that variable. 4 and 2, I've got 2 and 1. What that does do, though, is make this look like a quadratic equation, which we have some methods to solve, right? And in fact, I believe I can factor this. Of course, the only way to get u squared is u times u. What are the two numbers that go last? Anybody? Well, are those numbers both positive, both negative, or one of each? Both negative, I agree, because they have to multiply to be positive, so they have to have the same sign, but they had to be negative, so they have to both be negatives. What are the numbers? I'll start thinking of numbers that multiply to be 36 until you find the ones that add to 13, right? 9 and 4, of course, except, of course, obviously, negative. So negative 4, negative 9, or negative 9 and negative 4, doesn't matter. Okay, then what are the two solutions to this equation? Yeah, u equals 4. 4 is the number that makes the first factor 0. U equals 9. 9 is the number that makes the second factor 0. Now, but remember, this is not the equation we're trying to solve. This one is. But what we do now is look back up to where we made our substitution. This says u equals 4. But what is u actually? U is really x squared, right? So u equals 4 really says x squared equals 4. And u equals 9 really says x squared equals 9. So let's go ahead and finish finding the solutions, then we'll talk about why I did this. Yeah. So let's go ahead and finish solving the thing, and then we'll talk about why I did this substitution and where that helped us. So we know how to solve these. We can just take the square roots of both sides, right? Remember that 4 has both a positive and negative square root, and 9 has both a positive and negative square root. And so I get x equals plus or minus 2, and x equals plus or minus square root of 9 is 3, so plus or minus 3. And there are our 4 solutions. So a few things. Let me see if I can zoom out a little bit here so I don't have to keep moving this around so much. Okay, so a couple of things. First, let me see if I can get that to focus. First of all, notice this was 4th degree. This equation was 4th degree, and sure enough, we have 4 solutions. -2, +2, -3, and +3. So the reason I made that substitution is simply because it makes this thing that was unfamiliar to us, right? We haven't been solving 4th degree equations. By making this substitution, and all we had to do to make it was to realize that x to the 4th is the same as x to the 2nd squared. And I have an x to the 2nd here. And so that gives me something squared and something to the 1st power and a constant term. And then that still looks kind of weird because x to the 2nd squared, x to the 2nd looks weird. But if I just replace all those x to the 2nd powers with u, I'm only doing this because it makes the problem easier to look at and easier to think about, right? Because now it looks like something we've been doing. We solved that. Then the only thing we got to remember is when we get here, remember what we're really trying to find are the values of x that make this original statement true. But that's simple to do if we just realize that u is x squared. And so we replaced x squared with u. It should make sense that at the end of the problem, we need to replace u with what it really is, x squared. And then those are equations we can solve, right? Are we okay there? And by the way, I'm not going to take the time to plug these into the original and check them. But if you do, you'll see they all work. Like with this type of problem, when you solve it, you should check your work in case you've made an arithmetic mistake. But you don't have to check your work because, oh, maybe this is one of those where I find all the solutions correctly, but some of them don't work. You know, if you didn't make any arithmetic mistakes, these will always work. You should still check them just to make sure you haven't made a mistake, right?
Do you mind scooting the
Right good
paper
there.
upwards?
Oh, up that way. I can't seem to zoom out enough to see everything at once. Is that still big enough to see on the screen?
That's
up
plenty
there?
good, thank you.
Okay. All right, everybody good? Let's do one more of these, and then we got to quickly move on to the next thing because time is fleeting. Let me come up with one. I was going to do one, but I want to do one where something kind of different happens. So hang with me because I think you might see it on the test. So what if I do... What if I do minus, I don't want to do 36 because I've already gotten there. What if I do this? I want to do minus 1 plus 9. I think that'll do what we need to see. Okay, so x to the 4th plus 8x squared minus 9. So I'm going to do just what I did a minute ago. I'm going to say that x to the 4th is the same thing as x to the 2nd squared plus 8 times, there's an x squared, minus 9 equals 0. So I'm going to make that substitution. I'm going to replace x squared with u. And so I guess I should write that out just so we, you know, it's probably good practice to write out what you've done just to help remind you at the end that you've got to go back and replace when you solve it and replace your u's with x squared, right? But when I do, that's going to give me u squared plus 8u minus 9. So u squared plus 8u minus 9 equals 0. And so that is quadratic. We ought to be able to solve that. Of course, u times u is the only way to get u squared. What are the numbers I'm going to need there?
-1 and 9.
-1 and positive 9?
Yeah.
That's right. Do y'all agree? Because everybody look what we're checking to make sure that's right. Does everybody see that -1 times positive 9 is -9, the last number? And -1 plus 9 is positive 8, the middle number. So that's factored correctly. So the solutions to this equation that's got u in it are going to be u equal 1 and u equal -9, right? Because -9 plus 9 is 0, right? But now we have to remember, back to our substitution, these u's really are x squareds. So u equals 1 really says x squared equals 1. And where this says u equals -9, that really says x squared equals -9. And so now I can find the values of x, which are going to be, of course, the solutions to this original equation. I can find those, again, pretty easily just by taking the square roots of both sides. And so, of course, the square root of x squared is x equals plus or minus the square root of 1 is 1. And over here, the x squared of x squared, of course, is x. What's the square root of -9?
-3.
-3 times -3 is equal to -9.
3.
Ah, 3i. The square root of -9 is 3i, right? Y'all just got to remember, anytime you take the square root of a negative number, you take the square root of the positive version of that number. The square root of 9 is 3, but there's always an I because that represents the square root of -1. And this is 9 times -1, right? That's not a real number. It's an imaginary number, 3i. But again, there are 4 solutions, -1, +1, -3i, and +3i. 2 of those solutions aren't even real numbers, but that's okay. We still can find them as long as we can just remember how to take the square root of a negative number. Everybody good there? Okay, last problem type in section 1.6. And then, of course, we've got to get a break in, and then we've got to get through that practice test. So let me grab all of these. All right. The last type of equation in section 1.6 are called absolute value equations. This is like the world's simplest absolute value equation. The absolute value of x equals 3. We got to figure out what do we replace x with to make this true. So somebody tell me a solution to this equation. Y'all are telling me there are 2 solutions, -3 and +3. Is that right? Because if we just want to make the statement absolute value of x equal 3 true, if I were to replace x with -3, this would be true. Do y'all agree? Because the absolute value of -3 is 3. Or if I replace x with +3, this statement will also be true, won't it? Because the absolute value of +3 is certainly +3. So there are 2 solutions, right? Okay, so this is like the world's simplest absolute value equation. I mean, several of y'all just looked at it and right away knew what the solutions were, right? What if we had one that wasn't quite the world's simplest absolute value equation? What if we had one that looks like this? So this is the absolute value of 3x minus 5 equals 7. Where students usually miss this problem is they usually find a solution, but there's more than one solution and they don't find the other solution.
We have 5 of those sides.
Yeah, here's what you got to think about. It's easy to figure out what you would plug in place of x so that 3 times x minus 5 is equal to 7, right? That's not hard. And that will give you a solution, but it won't give you the only solution. We saw here that it turned out that there were 2 different numbers that made it true. The same thing's going to happen here. I am going to use this really simple one that we just did as a model for how to do this one. So if you look back up here at this one we just did, if you really think about what we did, like when I wrote the solutions here, literally what I did is this expression inside the absolute value bars. Now in this equation, that expression was super simple. It was just x. But I did the expression inside the absolute value bars, x, equals, I looked at this number and I wrote the negative of that number. And that gave me one of the solutions. And then this expression that's inside the absolute value bars, which happens to just be x in this case, I wrote exactly that expression again, equals to this number itself, the actual number. I'm going to do the same thing here. Watch carefully, because what some of you are thinking I'm about to do is not what I'm about to do. I'll talk about that in a minute. What I'm going to do here is just what I did with this last problem. I'm going to write exactly what's inside the absolute value bars. Now this time that's not just x. It's the expression 3x minus 5 equals the negative of this number, negative 7, or I'm going to write a second equation, just like I did here. Exactly what's inside the absolute value bars, 3x minus 5, equals that number itself, positive 7. And I'm going to solve each of those equations, and both of the solutions I get will solve this original absolute value equation. Because here I'm going to find the number I would replace x with to make this turn into the absolute value of negative 7 equals 7. Well, that's a true statement, so whatever that number is must be a solution, right? And here I'm going to find what number I should replace x with so that what I get up here is the absolute value of positive 7, right? But that's also equal to 7. So both of those will give me solutions. Now what I didn't do, and this is what I want to make sure I point out to y'all, I always have a few students who want to do this. When they write these equations without the absolute value bars, instead of writing 3x minus 5, they want to write 3x plus 5. Do you see why a student might want to do that? Because they're thinking, oh, well, the absolute value always makes minuses pluses, right? It always makes negatives positives. I get that, but here's the problem with it. If you think that way, y'all just tell me what this is equal to. Like, just work it out and tell me what that's equal to, what number that is equal to. 4, I agree. Because 7 minus 3 is 4. And the absolute value of 4 is 4. I thought that this minus was supposed to turn into a plus. No, it doesn't, right? Like when y'all see it written like this, nobody makes that mistake. Because they realize this is kind of an order of operations thing, right? It's like sort of like the absolute value bars are like parentheses. You need to do what's inside there first. You can't just arbitrarily change that sign and then do the problem. By the way, if you did, you get 10, and that would be wrong. Everybody agree? So all I'm cautioning y'all about is I always have students who make that mistake where when they write these equations, in at least one of them, they'll think this minus 5 should be a plus 5. But notice I never changed anything of the expression that's inside the absolute value bars. What I changed is the sign of the number on the other side, right? Okay, and now we just need to solve each of these. So, and they're pretty simple, 1.2 problems. Add 5 to each side here. I get 3x equals negative 7 plus 5 is negative 2. and then divide each side by 3. And so we see that one of our solutions is x equal negative 2/3. And then on the other equation, I solve it kind of the same way, add 5 to each side. I get 3x equal what, 12,
Yes.
right?
Yes.
And then I divide each side by 3. And 12 divided by 3 is 4. So my other solution is x equal 4. And both of those will solve the original absolute value inequality. It's probably real easy if you just look at it to see that if you plug 4 in here, it's going to work, right? So y'all follow along with my bouncing thumb here. If I plug 4 in for x, 3 times 4 is 12. 12 minus 5 is 7. And the absolute value of 7 is 7. If I look at what happens if I plug negative 2/3 in. So maybe we'll just do that one. I've got 3 times x. Well, if we plug negative 2/3 in for x, minus, where is it? Minus 5. We've got all that in absolute value bars. And we need to know, is that equal to 7? Well, you see what's going to happen here. When I multiply 3 times negative 2/3, those 3's cancel. Do y'all see that? And I just have negative 2 minus 5. And isn't negative 2 minus 5 equal to negative 7, right? But the absolute value of negative 7 is 7. That's equal to 7. So you can see that both of these work. So the absolute value equations are also not like those square root ones. When you solve it, if you set it up correctly and don't make arithmetic mistakes, these solutions will always work. So again, you should check your work to make sure you haven't made an arithmetic mistake, but you don't have to worry about, well, I might have done everything right and one of these might not work. Y'all see what I'm saying? They'll always work if you've done it right. Okay, we're going to look at just a couple more of those and we're going to try to do it pretty quickly because I know we need a break. In this problem, what do y'all suspect is the first thing that I ought to do? Say that again.
Take the 11.
Move that 11 to the other side, so add it to both sides. Kind of like we looked at with those square root problems. Before you set your two equations up and solve them, you want that absolute value expression by itself on one side, okay? So yeah, I'm going to add 11 to both sides before I do anything else. And when I do, now I get the absolute value of 2x plus 3 equals negative 4 plus 11 is 7. Now I'm ready to set up the problem and solve it, right? I'm going to do exactly what I did a minute ago. I'm going to write two equations. Whatever's inside the absolute values, in this case 2x plus 3, equals the negative of this number, negative 7. Or what's inside the absolute value bar is exactly the way it's written, 2x plus 3 equals this number itself, positive 7. And of course, I just need to solve each of those equations. So we'll run through and do that. So when I subtract 3 on each side here, I'm going to get 2x equal negative 10, divide each side by 2, and I'm going to have x equal negative 5, right? Then the other equation. And you can see that these are almost the same. It's just the numbers are a little different because you're working with a negative here and a positive here. I'm going to subtract 3 on each side. When I do, I get 2x by itself equals 7 minus 3 is 4. And of course, I divide each side by 2. 4 divided by 2 is 2. So that's my other solution. Everybody see that?
Mr. North,
Yes.
that was just really fast. The top part, it's not 12x, that's the absolute value of 2x plus 3.
Yes, I'm sorry. That's, yeah,
Okay.
that's not 12. That's,
Okay, that's fine. I'm just trying to keep up.
yeah, sorry. Those are absolute value bars. Everybody with me there? As I said, my penmanship could use a little work. Okay, everybody see how to do this? These are actually easy, aren't they? One thing I want y'all to see, and this is something you're going to run into, and you're probably going to see it on the test. So let's look at this one. This is a real simple one. Notice what's inside here is pretty straightforward. That is the absolute value of x minus 5 equals -7. So what do I do? So we looked at a couple of these. What should I do here?
Plus 5.
You should do x minus 5 equals -7 and x minus.
X minus 5 equals -7 and x minus 5 equals 7, and then solve them. If I do, let's do that real quick and see what happens. Because those are easy equations to solve, right? Here you add 7 on the, add 5 on each side, you're going to get x equal -2. Here, when you add 5 on each side, I think you're going to get x equal 12. So if we haven't done anything wrong, those will both be equations unless I've made an arithmetic mistake. Somebody plug those in and tell me, somebody just check those real quick. Plug them in and tell me if those numbers, if either or both of those numbers make this original equation true.
I hate to sound dumb, but can you redo all of that? Because you left me so far behind on that little one. I don't.
No, it's a.
In this one or this one?
That one.
This one? Well,
It is correct. Both of them are correct.
hang with me a second, Christopher. So you're saying if I
Never
plug
mind.
-2 in here, I get a true
She-
statement?
Yeah, she explained it to me. Never mind. I was having a slow moment. My bad.
Hang on. Nobody get ready for break yet. We ain't done. So
He
you're
just
telling
said-
me that if you replace this x with -2, I get a true statement.
Yes, he just realized it was just one step.
You get a true statement, yes.
How much you want to bet me on that? I'm broke. I could use the money.
Can you just tell us what we're wrong and tell us how to do it?
Can you tell me when you plug -2 in here in place of x, what do you get on the left-hand side?
-2 minus 5 is 7.
-2 minus 5 is
-7.
-7. But this isn't x minus 5. This is the absolute value of x minus 5. So what is the absolute value of -7? Y'all see? I know y'all getting aggravated with me, but I also know that when I just tell y'all the answer, y'all aren't thinking. And then you'll ask me the same question on the next problem that we just talked about. So I'm sorry, I'm just trying to get y'all thinking about this, because on a test, I'm not going to be there to point out what's going on. Do you see that if I plug -2 in here, I'm going to have the absolute value of -7, which is 7, not -7. So that doesn't make the original equation true. How about 12? Does it make the original equation true? No, now y'all see what's going on, right? Because if I plug 12 in here, I get the absolute value of 12 minus 5. That's the absolute value of 7, which is 7, not -7. Can somebody tell me a little more generally what our problem is in solving this equation? Yeah, it doesn't have a solution.
Anytime there's a negative as your answer.
Yeah, y'all think about this. Can an absolute value ever be equal to any negative number? Can't, right? But here's the thing, and so Christopher, let me come back to what you were saying. I know I blazed through that pretty quickly, but really all I wanted y'all to see is when you've got something like this, if you're just kind of mindlessly going along going, okay, absolute value equation, I know what I do. I write what's inside here equals a negative and what's inside here equals a positive, and I solve them, and those are my solutions. Then you would be prone to do this, right? And then solve them and think you had your solutions. What you've got to be aware of is, and the only way I really know for you to do this fairly efficiently is you've got to be paying attention, and you've got to know that an absolute value expression can never be equal to any negative number, right? So anytime you see that absolute value expression equals negative whatever, you should just say no solution, pat yourself on the back, and move on to the next problem. Everybody see that? So do you agree that if I did have something like that on the test, that would be a super easy problem that nobody should miss, right?
Yep.
Like all you really have to do to not miss that is kind of be paying attention and know that absolute values can never be negative. Okay, let's take a break. I know we're running a little late. It's like 7:26 or something now. It is 7:26, so let's say 7:37. We're going to start back and we're going to start working through this practice test.